Hello, everyone. I am Joe, and I'm going to be walking us through Cramer's rule for my video today. Now, Cramer's rule is another method of solving systems of equations, and today we're going to be using it to solve this particular system of equations up here. Now, if you're in the class and think this particular system of equations looks familiar, that's probably because it is. This is from the second midterm. Now, I was less than confident with Cramer's rule at the time because I believe we just learned it. So I did not choose this problem, but I'm going to be revisiting and walking us through it today. Now, solving systems of equations has a lot of real world examples, and they range from stuff like economics to rocketry. Now, I believe every one of us has to have had an economics class either in high school or in college, and they often do something where they have you basically find where supply meets demand, and that is done by solving systems of equations like this, with one of them being supply, one of them being demand. But without further ado, let's get into this system of equations. So we have what we're trying to solve on the top here, and right below that we have the definition of Cramer's rule as shown in Boas. So this is straight from the book, and the book describes it in the form a1x plus b1y equals c1 and a2x plus b2y equals c2 for our two equations. And if you map that onto what we're trying to solve, you get values for a1, b1, and c1 of 3, 1, and 9, respectively, with this 3 in front of the x, the invisible 1 in front of the y, and the 9. And if you do the same thing for the second equation, you get a2, b2, and c2 as 2, 10, and 2, 2, and 10, respectively. Now, this could also be 1, 1, and 5. You could simplify, but I'm going to use it as it is here. And now we can move on to the next step, which is describing x. Now, the definition in the book describes x as c1b2 minus c2b1 over a1b2 minus a2b1. And if you map that onto our newly found variables, x turns out to be 9 times 2 minus 10 times 1 over 3 times 2 minus 2 times 1. And this simplifies to 8/4, which is 2. So now we have our x value, and let's do the same for y. So y turns out to be, using the same method, 3 times 10 minus 9 times 2 over 3 times 2 minus 2 times 1. You might notice the denominators are the same in both of these fractions. That's because they are the same in the definition as well. And simplifying again, we get 12 over 4, which is 3 for our y value. And just like that, our system of equations is solved. We have a point of 2 in the x dimension and 3 in the y dimension. Now, like I said, this kind of system of equations solving method is very useful in the real world, not only with stuff like economics and finding where supply meets demand. It's useful for maximizing efficiency in a lot of different fields. You can use it in engineering, basically to meet two different values that change. You can use it to maximize like fuel efficiency, stuff like that. Those kinds of applications are too complicated to get into here. But these things do have a lot of real-world application, and Cramer's rule is a pretty good way of doing it. And also, I have my references here. I basically have a YouTube video I think is very, it explains it very concisely. It is a good refresher if you need a refresher for this method, and I have the book from which I grabbed the definition of Cramer's rule here. Thank you. Now, in the spirit of the name Cramer's rule, I think it is only fitting to send off the semester with a Seinfeld impression. What's the deal with linear algebra? I might have seen a handful of straight lines in this entire class.